the last thing to do when it comes to macroevolution is to put this all into a time frame, to put it all into a complete set of circumstances where we can first of all understand when things happen and how we know that these things happen at that point of time. So what we're going to look at is geological time and the movement of the Earth. Well, it turns out when you look at macroevolution, it reflects to a significant degree the geological history of the planet itself, because there are many important geological episodes that occur on Earth that influence the organisms that evolved on it. Clearly, there's an interplay. I mean, we still are subjected to that today. When you have storms, when you have earthquakes, when you have floods, all those kind of things are still some of the things that impact humanity. And so some of the really large-scale issues in the geological history of Earth clearly affected the history of life on Earth. Now, in order for us to understand these impacts, what geologists have done is they've established what's referred to as the geologic time scale. And so this is looking at different events in real time when they occurred, but also putting together what kinds of living organisms occurred at that time. And the scale is divided into several epochs, large-scale events, large-scale time blocks, and those are subdivided into shorter periods. And each time you look at these, you can see that there is a change in the diversity of organisms. Now, the diagram you'd best look at in the book, because the one I describe here, display here, is obviously very small, too small for reading, but I want you to focus really on the colors, because the colors are going to be instrumental in understanding this. First of all, when you look on the left side here, there is a thin time scale, this area here. And this time scale, that shows you basically real time. Real time in years. And so way back here, this is where the Earth was formed. And depending on how you want to look at this, we can call this the time backwards. So we can say, okay, this is basically 4.6 billion years ago. And we'll talk about that date in a little bit. And for this entire period here shown in this brownish color, this entire period that goes from 4.6 billion years ago to about 540 something years ago, so let's call it basically 4.1 billion years, that's all this, 4.1 billion years in real time is that block. But in that really long block, which represent the majority of time that the Earth has been around, we only have a few key things that happened. The few key things that happen are things like oxygen beginning to accumulate in the atmosphere, the oldest animal fossils emerging. Those kind of things happen. Some very major, very basic kinds of things. And then we get to this threshold here. 543 million years ago, we have something called the Cambrian explosion. The Cambrian is this earliest time slot here, the Cambrian. And in this Cambrian, that is where we see fossils for the first time for all the major phyla, all the kinds of worms, all the kinds of crustaceans that you can think of. Everything emerged in the Cambrian. So for the first time, we had a really full, diverse fossil record. Now this period is called the Paleozoic. Paleo means old, zoic, zoological time. So this is the old age, the old animal age, if you will. And if you look at the actual time scale here, that old age, that lasted for just about 300 million years. That's what that time scale is. 300 million years. Not billion, million years. So it's very, very short compared to the 4.1 billion we just left behind. And if you want to call this something, perhaps you could call this one the age of amphibians. That's where some of the large carnivores were amphibians. Now then a switch occurred right here about 245 million years ago. There was a significant switch to the Middle Age. And this Middle Age, when you look at the time scale again, as you can see, this is even shorter still. This was only about 180 million years long. And those 180 million years, those we can call the age of the dinosaurs, or maybe in general the age of the reptiles. That includes dinosaurs. And so 180 million years. Now the rest of it, the Cenozoic, that's sort of the recent era, the recent time, 65 million years ago. That's it, 65 million years ago. And of this, we've been around 100,000 or so years. 100,000 years. It's not very much when you look at 180 million years of an age of reptiles, 300 million years the age of amphibians. I don't know if we can even call this the age of humans yet. Perhaps this entire era could be called the age of mammals. That would be okay. But as humans, with only 100,000 years behind our belt, there's a lot more to come. That's pretty clear. So this is the geologic time scale. And one of the things to note is when these transitions happened. And these transitions tend to happen when there is some major upheaval. 65 million years ago, that was the impact of a big meteor on the Yucatan Peninsula. And that's what ultimately led to the extinction of the dinosaurs. 245 million years ago, the land on Earth was all in one big block at that point, and it started to break apart. That's major upheaval in terms of earthquakes and volcanoes and things like that. Waters rushing in, forming new oceans. That whole time was pretty dramatic. So the geologic time scale gives us a lot of information. Now, why is this important? Well, it turns out that if we find things in the fossil record, we need to be able to time them, to add them to a timeline, because only then can it truly be an archive for evolution. And so we need to be able to figure out how long ago we have certain types of dinosaur bones in the fossil record, or fossils like the scorpion in amber, or extinct organisms like these ammonites. Or perhaps even organisms that are just now coming back out from the deep freeze. Over the last several years, we found, courtesy of global warming, a series of very nice mammoths, including baby mammoths, with really well-preserved features and really well-preserved DNA. In fact, I think there was somebody who is saying that you could actually have a mammoth steak if you wanted, because it's been frozen for so long. The other thing that's interesting is that whereas it is not possible to legally trade the ivory from elephants, there are no laws that prevent the trade of mammoth ivory. So if you find a big tusk, one of the problems now is that people find more and more mammoth tusks. In fact, there have been several hundred found just in recent years, and they're now being traded. So the ivory market is sort of coming back from the dead, as it were, when it comes to mammoths. Now, fossil dating is one of the key things that allows us to place the different fossils into this archive. And fossils are giving you a way to record chronologically when things happened in the fossil record. Now, there are two ways to age fossils. The first one of these is simply to give a fossil the relative age. And relative age means you're going to look at where in the rock layer it is relative to another kind of fossil. And the fossil that's above is the one that's younger than the one that's below. Because if you consider your garbage dump, right, yesterday's garbage is going to be below today's garbage. So that's the relative age. But we can also use something called radiometric dating to find out the absolute age of fossils. And this is actually not very difficult to do. Radiometric dating is something that we use physics to help us figure out. And what we know from physics is the decay of isotopes. Radioactivity is a very well established concept. We know how it works. We know that radioactivity means that certain things are emitted from radioactive materials, and these radioactive materials over time decay to some other isotopes. And in radiometric dating, what you can do is use this decay to track how long it takes. So here's an example given this graph. This graph is looking at carbon-14 versus carbon-12. Now normally carbon has an atomic mass of 12. And there are some isotopes, these have 2 extra neutrons, and so you end up with a slightly heavier carbon atom, and this is the one that's radioactive. And the radioactivity means that over time this is going to decay back to carbon-12. So what happens here, let's say that you breathe the air today, and in our air today we have a certain ratio of carbon-14 to carbon-12. So when you incorporate into your body a certain amount of carbon, based on the plants that we have out there today, you are incorporating into your body a certain amount of carbon-14 and a certain amount of carbon-12. Very tiny amount of carbon-14, but appreciable and measurable. Now the carbon-14 is going to decay over time, and if you no longer replenish the carbon-14, which basically means you stop breathing, then that carbon-14 starts to go down. Stop breathing, stop eating. The carbon-14 is going to go down because it decays. You're no longer replenishing it. And so this graph shows you how long it takes for 50% of this carbon-14 to decay. And it takes about 5,600 years. So that's called the half-life. The half-life of carbon-14 is about 5,600 years. Now for carbon-14 to decay by another half, it's going to take twice that long, another 5,600 years. And every time that is reduced by half, you get another 5,600 years. And so when you get to, about this level here, then you realize, okay, this is no longer very accurate. There could be an error here because this is such a small amount. So carbon dating like this is probably good for maybe about 30,000 years. And that's enough time to date some of these mammoths, to date Egyptian mummies, to date a variety of plants that are no longer around. So it helps us with a lot of our tasks. And so if you look at an actual organism, here's a clam in this case, and as long as the clam is alive, it incorporates carbon-14 and carbon-12 from the environment into its shell. So here is illustrated in terms of what carbon-14 is, the little blue dots, those are carbon-14 atoms. And everything else in the shell is carbon-12. Now, as you see, once the clam has died, it does not add any more carbon, and the carbon-14 begins to decay. Therefore, you're now seeing fewer of those blue dots. And then lastly, let's say that somebody finds it after a certain amount of time. There are now very few blue dots, but because we know how fast carbon-14 decays, based on this ratio, we can actually figure out how much of this carbon-14 is reduced. So if only, let's say, 25% is left, that means it's gone through one half-life and another. So you'd say, oh, it's about 11,200 years ago that this clam died. And so that's what you can do. Now, obviously, when it comes to carbon, and you're only looking at 30,000 years, that gives you a limit to how far back in the past you can go. And that's why people use other things, for example, potassium-40, or even longer kinds of things, as we'll see in a little bit later. But you can use cobalt, you can use uranium, there's a variety of things that you can use, and it all helps you depending on what time frame you're actually looking at. Now, this has led people to a better understanding of the rocks and how the rocks move. It turns out that when you look at the continents today, with some not even so sophisticated types of measurements, you can track continental movement. And there's no doubt that the continents are moving. In fact, they used to be a single landmass. Now imagine for a moment that all the land on Earth form a single continent. It is known down here as Pangea. And Pangea was all one. So the entire landmass on the planet was in one area, which means everything else was just water. Now clearly that gives the planet a very different look, because the land is warmer than the water, and so you had a warm area and a cooler area. Now things are much more evenly distributed, and so you now have a different spread of climate on the planet. So climate change has been with us just based on the way the planet works. Now, 250 million years ago, this supercontinent, Pangea, was formed, and it then began to break apart. As it forms, it creates volcanism and earthquakes, and as it breaks apart, it creates them again. And so, for a period of time, probably in the order of several dozen million years, you find that there was a lot of climate change, along with geographic isolation being produced, and as a consequence you could end up with allopatric speciation, and some of these things are still with us today. For example, when South America and Africa split up, here's Africa and here's South America, there are now different organisms, things like lungfish, for example, that exist in parts of West Africa and in parts of South America and nowhere else. Well, they didn't swim across, but because it once was the same area, they simply ended up on two sides of the different continents. Now, you can end up on two sides of different continental plates here, too. You stay here and live in the high desert, or you go to the other side of Cajon Pass, and then you're on the Pacific plate. And that will eventually allow you to travel without moving all the way to the Pacific Northwest. It'll take about 75 million years or so, but that's how it's going. At a certain speed, you know. So these are the kind of things that are with us today. Plate tectonics, macroevolution. This is what Pangea looked like. This is sort of a more detailed image with the continents that we know today marked in it. Now there are a couple of surprises perhaps. One surprise is that Australia is here, Antarctica is there, and India is over here. Wait a minute, India next to Antarctica? That's not where it is. No, it's because India actually started to travel and then slammed into Eurasia. So it's moving in a different way than you may think. So there's all kinds of interesting things that happen. Now it turns out that way back in 1912, Alfred Wegener looked at a variety of data that he found, and he was also taken by the shape of the continents. And if you look at the continents as a puzzle piece, you'd find that things do fit together. Yeah, maybe not so perfectly, but for every little nook there is an open corner, if you look carefully. And so Wegener was somebody who thought that these continents moved. He proposed something called Continental Drift. And as with many ideas that are ahead of their time, he was ultimately being ridiculed because nobody could conceive of this. Even though he said, well, it makes sense because we do observe volcanic activity in certain areas, and that's where I think these plates are actually moving, and that's what causes earthquakes. So he was very good at observing these things and putting it together, but nobody believed the story because there was no mechanism for it. The mechanism for continental drift wasn't there until in the 1940s, during regular radar tracking and depth of seafloor measurements as part of what the fleet was doing in the Atlantic, people discovered that there was a mountain chain in the mid-Atlantic. We call that the MidAtlantic Ridge. And it was surprising because people didn't think to look for mountains in the middle of the ocean. I mean, why would you have mountains there? Mountains are sort of a land thing, aren't they? Well, it turns out that we've learned since then that these mid-Atlantic mountains, that ridge, is actually a spreading center. And it is a spreading center because there are small amounts of new crust being formed all the time, right there in the mid-Atlantic. There's actual geologic movement down there, and you can go and look at it and you can measure it. And that is what forces the coasts of Europe and North America apart. Not that fast, centimeters every year, but that's still something you can measure, right? I mean, think about moving something a few inches. You can move a table a few inches. There you go. That's how far away this year the North American coast and Europe will be moving apart. Just what I just moved the distance, I just moved the table. It's one of those small incremental changes. It's the kind of change that over time can make a drop of water drill a hole in a rock. Now, if you look at the Seismic Hazard Map, this is not a map that you have in your books. This is one that I picked up to illustrate this point. You can actually identify, based on the earthquake activity, the edges of some of these plates. So there is the Pacific plate, and there is the North American plate, and they have their edges right where we are today. We are right near that very edge, Cajon Pass. That's the San Andreas Fault, and it is that big fault line. Now, if you go to other places along the Pacific Rim, you'll find that this Pacific plate's border can be very easily identified by looking at where the volcanic chains of volcanic eruptions are. It's that so-called ring of fire right around the Pacific that marks the boundaries of the Pacific plate. Now, of course, there are some other interesting areas where the Earth is moving. One of these is the Himalayas. And look at this entire area, not just the Himalayas, but all this area of Iran here, northern India, and well into places like Myanmar. And that's because this entire area here, called India, sits on its own little plate, and it's moving north. And it crumples everything in its path. It's kind of like, if you have a a collision with your car, it crumples up the hood. It's that same kind of pressure that crumples up the hood that's crumpling up the mountains. And just as we can measure how far and how fast every year these coasts are moving apart, so can we measure that these mountains are still rising. Things like measuring Mount Everest has never been more fun, because now you can actually tell to the inch if there is an increase. Mount Everest, when it was first measured, they used a technique that made it appear to be a little bit smaller than it actually is. Now they've got it at the right elevation. I forget what it is, 29,000 feet or something like that. And it's gone up a little bit. Not by a huge amount, not by feet, but by an inch or two. And because of our data collection now using satellites and GPS, the information gets better and more precise, and so we can actually detect changes. The Mid-Atlantic Ridge that causes a lot of this is literally in the middle of the Atlantic. And it is a remarkable mountain chain because it is actually the area where the Earth splits. Now, it splits not open, but it splits because that's where currently all these plates are getting their energy to move from. So it's that Mid-Atlantic Ridge that issues a little bit of volcanic material every day, and it forces the continents apart. So the Mid-Atlantic Ridge is what gives us the energy, what transmits the energy from the inside of the Earth to the continents, so that the continents literally are shifting. This is just like the skin on top of the milk, the hot milk. You can move that skin around a little bit, and you can push it together, and it will crumple like that. That's the mountains of the Himalayas. They're crumpling, and you can play with that next time you drink hot milk. But that's basically what happens with the Mid-Atlantic Ridge. It gives you the energy to have these continents move. And it's pretty interesting to put it all together. So once you know how things work, and once you see that these kind of things exist, then you suddenly realize, well, it's obvious that things are going to change, and that's just the mechanism.